I was looking at thumbnails of my videos and I realized I kind of wear the same couple of shirts each video. It's not because I just wear the same clothes. I promise I wear other clothes. I guess it's just a coincidence that I just wear the same shirts. I don't know. But what we're going to do is we're going to derive the equation for centripetal acceleration, or it's the magnitude of centripetal acceleration for an object in circular motion. And I'm going to do it with calculus. There is a way to do it in a more conceptual way. There is a way to derive it. It's a pretty interesting, it's a really cool derivation, honestly. If you search up Khan Academy, they have that derivation open. Maybe I'll make a video, but I want to focus on the calculus just because I think it's so cool seeing the calculus bridge with the physics. Let's say you have an object moving in circular motion, right? This object is moving about an origin, right? So we could say, if it's moving in space, it's centered around the origin, and it has a mass m and then a radius r. Sorry, I have the sniffles. And we want to find, what's the magnitude of the centripetal acceleration. One thing we can do is we could give two equations for motion for this scenario, because an object moving in circular motion is moving in the x-axis and the y-axis simultaneously. And those equations are given by, like, x of t equals r sine omega times time, and y of t, right? So the x position as a function of time and the y position as a function of time are cosine omega times time. I didn't pull these equations out of thin air. Where they come from, it's from parametrics, which I'm guessing if you know calculus, you're familiar with parametrics. But the idea being that, well, I know by the Pythagorean identity, sine squared omega times time plus cosine squared omega times time, that's going to equal 1. Well, what is sine squared? Well, I know sine omega times time is just x of t over r, right? When I solve for sine omega times time. Same thing here, y of t over r squared equals 1. So then, I would obviously, I would have something like this, right, when I distribute the square, and then I just multiply everything by r squared onto both sides, and I get an equation for a circle. X squared plus y squared equals r squared. So this is the form of a circle. So that's how I know that, hey, these formulas describe this object's motion because it's moving in a circle with radius r. So using these equations, what I can do, remember, right, physics is a world of vectors. We deal with vectors a lot, and vectors help really quantify and describe a lot of phenomena. So what I could do is say, well, hey, the object's position vector from the origin, right? Its position vector is given by a function. I could say it's given by a function r of t. And what I could say is that, hey, r of t is really just equal to, if you've worked with vectors before, there's got to be an x component and a y component. Well, what's the x component? The x component of the vector just ends up being r, well, I guess it ends up being, oh wait, maybe I should have flipped those. Well, I guess not. I guess it depends what angle, right? Yeah, it depends, because this is like if the object started here, right? Because at t equals 0 and then it moved like that. But what ends up happening is it ends up equaling r sine omega times time as the x component, and then r cosine omega times time for the y component. The reason I was confused if it was flip-flop is usually with vectors, you look at like the angle to the horizontal, right? But in this case, we're actually looking at the angle to the vertical. So that's why. But don't worry about that too much. It's just we're just saying that, hey, the vector function has the same components as the parametric functions because x of t, right, is r sine omega times time, and then the y of t is r cosine omega times time. And first of all, I should clarify, what is omega? You might be like, what the heck? You just brought omega. I didn't explain that. omega is really the rotational velocity, because the deal is, for your trig functions, omega is 2 pi over the period. The reason it's 2 pi over the period is that way, you know how sine repeats every 2 pi? So 2 pi, 4 pi, 6 pi. Well, when we plug in t, right, if you were to plug in t, right, 2 pi over t multiplied by t, right, the t's cross off, so then you would be left with 2 pi. So that way it's like, it's sine 2 pi, right? Then it repeats, right? Because that's the deal with the period, right? It's when the object has repeated its motion and it's gone through a full cycle. And if you plug in 2t, you get 4 pi, right? 6t you get, or 3t you get 6 pi. So yeah, it ends up being the rotational velocity, because after a full rotation, 2 pi, that's like your delta theta, over t, right, the period, it's like kind of like theta over time, right? How much angle you swept out over time, 2 pi over t. So if you had a really fast period, that would be, that if you had a really fast period, right, really small, or a really small period, right, it would be a really big rotational velocity. So what we can do is actually just use Newton's second law. We know by Newton's second law, the net force on an object is going to equal the mass times the acceleration of that object. So we could take some derivatives to go from position to acceleration. So the first derivative, we would do velocity. So for your trig, this would end up being, you would have to use chain rule. So it would be r cosine, right? The derivative of sine is cosine, omega times time, and then multiply by omega, by chain rule, right? You take the derivative of the outer and multiply by the derivative of the inner function. Same thing here. So we would get negative r sine omega times time, and then multiply by omega. Now, if you were to take the acceleration, you do the same thing. So now I would get negative r sine omega times time. I believe so, right? I think so. The derivative of cosine is that, yeah, okay, I should be doing this right. Yeah, okay. Omega times time. I had the omega from earlier, and now I have to multiply by omega again, because we're still, that inner function hasn't changed. So I get omega squared, basically. And then same thing, negative r sine, or cosine, right? The derivative of sine is cosine. Cosine omega t, and then I would have that omega squared, because I end up multiplying by omega again. Okay, what I can do, just for giggles, I can actually pull the omega squared. I can actually pull the r, right? You know, with vectors, you can essentially pull out common factors, and I get this negative omega squared times r term factored out. And you might actually be able to see why in a second we are doing this. And then, oh, we pulled out the negative. Okay, perfect. So this is the acceleration. And so the net force, by Newton's second law, the net force on the object at any time would just end up being, I would just take the vector a of t and multiply it by the scalar omega. It ends up being a scalar multiple. So I get negative m omega squared times r sine omega t cosine omega t. Now you might be saying, what the heck? This right here, this acceleration, this is not the derived formula, right? Like, well, where's the v squared? Where's there's an r, but there's this weird vector. Remember, this is like the vector formula for it, right? We haven't found the magnitude of acceleration yet. The way we do that is we would take, so let's just go to acceleration here, right? So what we can do is we could say, hey, actually, I guess we should do it with force. Let's do it with force. Why not? Because I want to show you this in a second. Okay. What I know is that the magnitude of F, Or let's do acceleration. I guess this part with the force wasn't really necessary. The way I was going to do this derivation, I was doing it a little differently. It's fine. We're just going to deal with acceleration. So if I take the magnitude of a of t, this is the same as essentially doing, so I guess we should distribute these to its parts, because we're going to do the x component squared plus the y component squared of the acceleration. That's how you find the magnitude of anything, right? Of any vector, right? Using Pythagorean theorem. X component squared plus y component squared gives us the total length of that vector squared. So the magnitude will end up being the square root of the magnitude. I use the absolute values for that. It's going to equal square root omega squared, negative omega squared r, and then sine omega t squared plus negative omega squared r cosine omega times time squared. Now, I can factor out the omega squared term, and when I end up squaring this out, the negative will actually go away. So I essentially get this term squared times sine squared t plus that omega squared term times cosine squared. Right? When I pull out, factor out the omega squared r term, I get sine squared omega times time plus cosine squared omega times time. And that's brilliant, because this is just the Pythagorean identity. This just becomes 1. So when I take the square root, right, this square root cancels out with the square here. I get that the magnitude of the acceleration is equal to omega squared times r. And to get this into a form we're more familiar with, you just got to remember, hey, omega is really equal to v over r. The reason for this, or I guess I should write r, I could say r omega is equal to v. What's a good way to explain this? The way I always like to think about it is, well, I know theta, the amount of your change in theta, I guess, right? The amount of theta you've swept out is really equal to the distance traveled over r, or r times change in theta. This is just the arc length formula, right? Because for this change in theta multiplied by r, this gives you the arc length of that part of the circle. So when you divide both sides by time, or take the derivative with respect to time, you just get your r omega equals v. So, hey, this is the same thing. Omega squared is therefore the same thing as v over r squared times r, and this gives us v squared over r. And then if you were to do the same thing with force, you would get the same thing, but then you get mv squared over r. So that tells you the net force is really equal to m times v squared over r, which is the acceleration. So f equals ma. It all works out. So yeah, this is hopefully a pretty interesting derivation using some calculus. And yeah, thank you for watching.